Now let us discuss some of the numericals so that we will have a good understanding of the concepts. Let us see the first question. There are three registers R1, R2 and R3 having the values 10 kilo ohm, 14 kilo ohm and 24 kilo ohm respectively, and RMS noise voltage of one of the resistor, that is R1, is given, that is 0.3 microvolt. It is the RMS value of the noise voltage for R1. The question is, if these three resistors are connected in series, then what is the overall thermal noise voltage that we will see at the output terminal? And if these resistors are connected in parallel, then what is the value of output thermal noise voltage? So what is given is thermal noise voltage across R1 or of noisy resistor R1. So V1 square, that is a mean square value of the noise voltage due to resistance R1, that is equal to the 0.3 microvolt, the whole square, because 0.3 microvolt it's RMS, so I have to square it to make it mean square value, and this mean square value, by the definition, it should be equal to 4 kT B times R1. So what we know is the value of R1, that is 10 kilo ohm. So this term, that is 4 kT B, I can find it by dividing this value by R1. So this is going to be 9 into 10 power minus 18. So let us see if these three resistors are connected in series, then by using the method 2, because I can use method 2 to solve this problem, because it is understood from the problem that all the resistances are at the same temperature. So method 2 is applicable in this case. So if they are in series, then the R equivalent can be found as R1 plus R2 plus R3, and that is equal to 10 plus 14 plus 24 kilo, and this is the value of R equivalent, which is 48 kilo ohm. Now by using the step number 2, I can write that mean square value, that is overall mean square value of the noise voltage due to series connection, is equal to 4 kT B R equivalent. So we know the value of 4 kT B from this, that is equal to 9 into 10 power minus 18, and the R equivalent value due to series connection is 48 kilo ohm. So I can multiply this R equivalent with 4 kTb, I get the value of 0.432 into 10 power minus 12 volt square. Now I am interested in the RMS value that is developed across the series connection. So that is equal to Vn, and this is nothing but square root of this quantity. So I get this equal to 0.66 microvolt. Now if these resistors are connected in parallel, then it is better to first find G equivalent, and then in second step I can find mean square value of the current instead of mean square value of voltage. So again applying method 2, but doing Norton equivalent, that is G equivalent. Since these resistors are connected in parallel, so conductance are going to be added, and that is equal to G equivalent, that is overall conductance. So G1 is nothing but 1 upon R1, and R1 is nothing but 10 kilo ohm. G2 is nothing but 1 upon R2, and R2 is nothing but 14 kilo ohm. And G3 is nothing but 1 upon R3, and R3 is equal to 24 kilo ohm. If you calculate this sum, you get 0.213 milli ohm inverse, or you can call it mho. Now by using the second step, which says that mean square thermal noise current, that is IN square, is given by 4 kTb G equivalent, and since we know this 4 kTb from this derivation, and now we know G equivalent as well, which is nothing but this one, when I multiply these two terms, I get 1.917 into 10 power minus 21 ampere square, and from this I can find the RMS current, which is nothing but square root of this quantity. So I get 43.8 picoampere. So once I get root mean square current, I can find root mean square voltage as well by this relationship, which is nothing but Ohm's law, that is I into R, and this is IN, this is RMS current into R equivalent, and R equivalent is nothing but 1 upon G equivalent. So this becomes IN upon G equivalent. So IN is nothing but 43.8 picoampere, and G equivalent is 0.213 millimho. So I get 0.20 microvolt. So these are the two results if they are connected in series and in parallel. So if they are in series, then the overall RMS noise voltage is 0.66 microvolt, and if they are connected in parallel, then overall RMS noise voltage is 0.20 microvolt. Now let us see the second numerical. Now in this case, these resistors are neither in series nor in parallel. Instead, if you see this circuit, we have again three resistors, R1, R2 and R3. R1 is equal to 10 kilo ohm, R2 is 20 kilo ohm, and R3 is 30 kilo ohm, and given the temperature is 290 Kelvin and the bandwidth of observation is 100 kilohertz. So since all these resistances are at the same temperature, so I can use method 2, which is more easier as compared to method 1. So let's go with the method 2. Method 2 says that the first step, you need to calculate R equivalent by looking at the output terminal into the circuit. So if you see from the output terminal, you will see that R1 and R2, they are connected in series, and this series combination of R1 and R2 is in parallel with R3 if you look from this point, this terminal A and B. So R1 plus R2 in parallel with R3, that is nothing but R equivalent. So R equivalent is nothing but R1 plus R2 in parallel with R3. So we get this one. So R equivalent is going to be this. R equivalent is equal to 15 kilo ohm. You can solve it, that if they are in series, so I get 10 plus 20, that is 30 kilo ohm, and R3 is 30 kilo ohm. So 30 kilo ohm in parallel with 30 kilo ohm, I get 15 kilo ohm. So this is the result of R equivalent. Now the second step, overall noise output noise voltage is found by using this relationship, that is nothing but mean square voltage VO square overall mean square noise voltage is equal to 4 kTB R equivalent, and we know what is K, which is nothing but a Boltzmann constant. So this value is 1.38 into 10 power minus 23 joules per Kelvin. Temperature given is 290 Kelvin, and the bandwidth given is 100 kilohertz, and R equivalent, which we have calculated as 15 kilo ohm. When you do this calculation part, you get that mean square overall noise voltage is equal to 24 into 10 power minus 12 volt square, and when you take the square root of this mean square value, you get the RMS thermal noise voltage, that is equal to 4.9 microvolt. Now let us see the numerical number 3a. Again we have two resistances which are in parallel, but now in this case these two resistances are kept at two different temperatures. R1 is kept at temperature T1, which is equal to 290 Kelvin, and R2 is kept at temperature T2, which is 400 Kelvin, and R1 value is 10 kilo ohm and R2 value is 20 kilo ohm, and the bandwidth of observation is going to be 1 megahertz. So in this case we cannot apply method 2, we have to use method 1 to solve this thermal noise voltage at the output terminal. If you see the step number 1, it is replace all the noisy resistor with their Thevenin equivalent. So let's apply step number 1. So we get R1 replace with its Thevenin equivalent. So it's a R1 which is noiseless, and V1 square, that is the mean square value, noise source, and that is equal to 4 KT1 BR1, and the same with the R2. So this is noiseless R2, and in series there is a thermal noise voltage due to this R2. So this is V2, that is equal to, let me write V2 square, that is equal to 4K, now in this case T2 BR2, and we are interested in finding the overall thermal noise voltage between these two terminals. So this is step number 1. Step number 2, it says that calculate output voltage due to each one of these sources. In this case it's V1 and V2. So when you consider V1, I get VO1, but in this case I have to short this V2, and when I find VO2 due to V2, then this V1 source should be mute. So let us find VO1 first, In this case, this V2 should be short circuit, and now this is VO1, and this VO1 is nothing but the voltage across R2. So I can find it by using voltage divider rule, that R2 upon R1 plus R2 into this V1, and V1 is nothing but 4KT1 BR1. So you can see here, that is VO1 square is going to be 4KT1 BR1. This is V1 square, and this is due to the voltage divider rule, that is R2 upon R1 plus R2 and the whole square. Similarly, we can find VO2 due to V2, and in this case V1 should be 0, which is nothing but I have to replace this V1 with short circuit. Now I am interested in finding VO2 due to voltage V2. So now I have only V2. In this case, if you see, VO2 is now the voltage across R1 and the total voltage is V2. So by using voltage divider rule, VO2 is nothing but R1 upon R1 plus R2 into V2. So this is V2 and this is R1. When you square it, it's going to be V2 square and R1 plus R2 the whole square, which is this values. So this is my V2 square and this is R1 upon R1 plus R2 the whole square. When you calculate these two values, VO1 square and VO2 square, we get this values. Now the last step is to apply superposition of mean square values. So the overall mean square voltage is equal to the sum of individual mean square voltage at the output. So VO1 square we have calculated to be this quantity, and VO2 square we have calculated to be this quantity. When you rearrange these two terms, you get 4K times T1 R2 plus T2 R1 divided by R1 plus R2 into B times R1 R2 divided by R1 plus R2. So just by adding these two values, I can find the overall mean square voltage at the output terminal to be equal to 1.202 into 10 power minus 10 volt square. And when you take the square root of this quantity, you get the overall RMS noise voltage, that is equal to 10.962 microvolt in this case. Now let us see numerical 3b. In 3a we have seen two resistances connected in parallel but at two different temperature. Now in this case we have two resistances connected in series but now at again two different temperatures. So R1 is 10 kilo ohm and it is kept at temperature T1, that is 290 Kelvin, and R2 is 20 kilo ohm kept at the temperature 400 Kelvin, that is T2, and the bandwidth of observation is again 1 megahertz. So again, by the same argument, we can say that method 2 is not applicable in solving this problem. Instead, we have to use method 1 to find out the overall RMS noise voltage between the terminal A and B. So again, we have to replace this R1 and R2 by their Thevenin equivalent. So this is R1, which is replaced by its Thevenin equivalent. So this is noiseless R1 and this is V1, and again it is square root of 4KT1 BR1, and in the second case it's going to be V2, which is RMS noise voltage due to the resistance R2, and here we are interested in finding this overall noise voltage between this terminal A and B. This is step number 1. Step number 2 says that you find VO1 due to V1, and in that case you short circuit this V2 and then find VO2 due to V2, and in this case you have to switch off this V1. So it means you have to short circuit this V1. So if you see VO1, when you short circuit this V2, what you observe? You observe that there is no current flowing through this circuit because this A and B are open circuited. So in this case, the drop across this R1 is 0 and drop across R2 is 0 because there is no current through this circuit. So this VO1 is equal to V1 in this case, and VO2 is equal to V2 by making the same argument. So when you square it, you get the mean square voltage, mean square output voltage due to V1 and mean square output voltage due to V2, and they are same, they are equal. So V1 square is nothing but 4KT1 BR1, and this is VO2 square is nothing but 4KT2 BR2. So which I have written here, that is VO1 square, and that is equal to V1 square itself. So 4KT1 BR1. If you calculate, you get this value. When you calculate VO2 square, you get this value, and this VO2 square is equal to this V2 square itself. Now, on applying third step, the overall mean square voltage is nothing but the addition of individual mean square voltages. So when you write this 4k T1 BR1 and 4k T2 BR2 here, you can take common, that is 4kB, 4kB. What remains is T1R1 from the first term and T2R2 from the second term. So this is T1R1 plus T2R2. And when you plug all these values, you get overall mean square voltage equal to 6.0168 into 10 power minus 10 volt square. And when you take the square root of this, you get 24.53 microvolt.